In the 1980s, Mark Harrison and Bruce Watson were in Jack Hills, Australia, when they found something that would basically rewrite Earth's history. But they didn't know what they'd found for about 20 more years, because they had to wait for our technology to catch up and be able to actually analyze their find properly to discover something incredible. I'm Sparrow, and I'm a science communicator with a background in behavioral science and pedagogy. And today's video is about atmosphere. What Harrison and Watson found in Jack Hills, Australia was a crystal of zircon. This crystal was only about the size of a grain of sand, and actually smaller than most grains of sand. But what it lacked in size, it made up for in age by being the single oldest object ever found on this planet. And one of the oldest objects ever found in our entire solar system. This zircon, known as the Jack Hills zircon, was 4.4 billion years old. Prior to the finding and accurate dating of this zircon, we didn't even know this planet was that old. However, we knew that the solar system had been around for at least 4.6 billion years, because that's how old the oldest object we'd found in the solar system was. So as of now, we know that Earth is between 4.4 and 4.6 billion years old. But that wasn't the most important thing about this crystal. Zircon is made out of 3 elements: zirconium, silicon, and oxygen. And if you're like me, oxygen sounds pretty important. It's kind of the thing we breathe. And you're right, oxygen was the important thing about this crystal. Specifically oxygen 18, which is only absorbed by rocks that form when lava cools underwater. Which means that 4.4 billion years ago, when this planet was still basically a newborn baby planet, it had liquid water. And when a planet with high tectonic activity, which we know Earth has today and definitely had in the past, has liquid water, that means it also has water vapor in its atmosphere. Now for clarity, we have never uncovered any evidence to suggest that there was life on our planet 4.4 billion years ago. In fact, that was the start of what's called the Hadean Eon, named after Hades, as in hell, because the planet was basically a ball of molten rock, recently molten rock, and boiling oceans. And what little we do know suggests that the atmosphere would have been made of carbon dioxide, water vapor, methane, and ammonia. So not exactly something you or I would want to breathe. However, this atmosphere was changing. One factor for that change, of course, was tectonic activity, because when the fault lines and volcanoes spit out lava, they also spit out gaseous emissions, which go into the atmosphere and start making changes. In addition, solar radiation and radiation from space was breaking apart some of those compounds and allowing ions to form, which would then bond with other ions and form new compounds in the atmosphere. This process slowly altered the atmosphere of the planet until it became something that was able to filter and reduce the extremes of temperature and radiation to the point where life could form. And we know that because life did form. The light side, dark side of the moon doesn't mean what you think it means, because people on Earth use those terms differently than people in space. When you're standing on planet Earth, the light side of the moon is the side that faces Earth and you're able to see it. It's light because it's known, whereas the dark side is the side facing away and unknown. But when you're in space, the light side of the moon is actually the side with the sun's light coming down and touching it, and the dark side is the side where the sun's light does not touch it. And so, while on Earth, the light side and dark side don't change because the same side is always facing Earth due to the speed at which it orbits and spins, the light side and dark side, as compared to the sun, do change, which makes these numbers a lot more terrifying. The highest temperature on the moon is 121 centigrade, or 250 Fahrenheit, whereas the lowest temperature, there's a caveat to that, the lowest changeable temperature on the moon is 133 below 0 centigrade, or 208 below 0 Fahrenheit. However, there is a lower temperature on the moon because there is a spot in a crater on the dark side that actually never sees sunlight, and that temperature is negative 410 degrees Fahrenheit. To add some perspective on those temperature variances, I went ahead and looked up the global high and low for Earth today, the day that I'm recording this, not necessarily the day that I'll actually get it edited and posted. But today's lowest temperature was 89 below 0 centigrade, or 129 below 0 Fahrenheit in Antarctica, where it was measured by the scientists who spend much of the year down there taking various other measurements. And the highest temperature measured on our planet today was 56.7 centigrade, or 134 degrees Fahrenheit in California, in a place where people actually live. Our atmosphere changed into something that would turn those crazy space temperatures into temperatures more similar to what we have today. We have no evidence of life during the Hadean era, the Hadean eon. Eon meaning set of 1 billion years, roughly. However, during the Archaeozoic era, that changed. In Greenland, fossils of single-cell organisms were found that dated back to 3.7 billion years ago. These life forms were the ancestors of modern bacteria and archaea. Now, I broke it down because I was curious what's the difference between a bacteria and an archaea, and the answer is oxygen. Bacteria consume sunlight and produce oxygen, photosynthesis, whereas archaea consume sunlight without producing oxygen, phototrophs. There's also ones of both groups that consume inorganic mineral compounds, lithotrophs or chemotrophs, and ones that consume organic compounds, known as organotrophs. And yes, back then, that did mean cannibalism. Now, these creatures continued to modify the atmosphere with basically the equivalent of their farts. Some of them were producing oxygen, which then of course went into the atmosphere. Some were producing carbon dioxide. Some were engaged in what's called nitrogen fixing, which is when they take free nitrogen from the oxygen and bond it to other matter. They were changing the atmosphere, and those changes caused changes to the climate and conditions on the planet. By the Proterozoic era, oxygen was freely available in the atmosphere. And we know this because oxygen hates being alone. Oxygen will only be by itself if it doesn't have other options. And some pretty common options during the early age of Earth was metal. Basically, oxygen found in the atmosphere today, or the ocean, or water, or really anywhere, will latch on to metal ions and create oxidization, or rust. Oxygen will bond to the hemoglobin in your blood, or if you were a horseshoe crab the copper equivalent. It's really cool and kind of destructive and traceable. See, we could see over the course of time in rocks of various ages steadily increasing levels of oxygen in the stone. That includes things like feldspars, which are high in iron and other metals, having more and more rust elements in them. Things like turquoise, which is basically oxidized copper in stone, and also higher and higher rates of quartz related, which is silicon tetraoxide minerals. And we saw these steadily increasing levels up until the stone was completely saturated or full of oxygen. And at that point, Earth underwent what's known as the oxygen cataclysm. About 2 billion years ago, the atmosphere had enough oxygen in it that it killed almost every single living thing on the planet, which of course at this time was just single-celled organisms like anaerobic bacteria and archaea. With more than 95% of life on this planet dead, the atmosphere went through another change, and so did life on the planet. Enter my personal favorite, mitochondria. Now, I know what you're thinking. You're thinking, I've heard of that. Mitochondria is the powerhouse of the cell. And you're right. It is, and this is the same mitochondria as that. Originally, mitochondria was its own organism, a single-celled organism that consumed oxygen, and that set it apart from everything else on the planet. It also made it kind of an overpowered ally for anything that wanted to survive. See, the remaining bacteria and archaea on the planet were still sensitive to oxygen and in danger from the atmosphere they were creating. So they needed to buddy up with mitochondria in order to have someone protect them from the oxygen. This worked out great for mitochondria, especially when it teamed up with photosynthetic organisms like chloroplasts. The organism would consume what it needed, like sunlight, and produce oxygen, and then feed it directly to the mitochondria, which would then produce energy-granting compounds that it would feed back to the chloroplast. This was such a great system that it just never stopped. And to this day, we, humans, have mitochondria living in our cells, sharing DNA with us because of that 2 billion year old friendship. With that system in place and the barrier of oxygen conquered, Earth was ready for the Cambrian explosion. We touched on the topic a bit in a previous video on plate tectonics and Pangaea, and it's important to note that this was basically the flag, so to speak, that marks the beginning of the Phanerozoic era, the Phanerozoic eon, which is the eon of visible life, the eon that we're in right now. And I know what you're thinking. You're thinking, this video is supposed to be about the atmosphere, but we talked about ancient crystals, and we talked about single-cell organisms, and we talked about mitochondria being the powerhouse of the cell, and now we're talking about the Cambrian explosion. But I promise I have a point, because all of these things have worked together to change our atmosphere over billions of years. And that atmosphere, in turn, changed them. The things we know about dinosaurs and other early life as found in fossils from the Cambrian explosion and afterwards the various eras, Jurassic, Triassic, Cretaceous, all of those things, in addition to telling us about all the cool animals that lived on our planet, tell us more about the environment where they lived. We know about when there were major volcanic activities because of the difference in the gases found in rocks and the well, not gases, but the compounds stolen from gases found in rocks and the ways that things died during those times. And what we know is that the climate, moisture, and specific gas contents of our atmosphere fluctuated based on tectonic activity and the species present on the surface of the Earth and in the oceans at that time. And even before humans first started walking on two legs, we know that carbon dioxide was making its presence known. Pre-humanity, carbon dioxide kept the Earth warmish by trapping and distributing solar heat. It also kept it from getting too hot in one particular spot, the way the moon does. We also know that any time that carbon dioxide trapped heat caused global temperature variances in excess of 7 degrees from the global temperature average, there was a major die-off of life on the entire planet. I do want to digress and just talk a little bit about what the global temperature variances and global temperature averages are. What they do is they calculate the global average temperature by taking measurements all over the globe and averaging them. So as of the day that I'm writing this script, the global average temperature is 15 degrees centigrade or 59 degrees Fahrenheit, whereas the lowest temperature, if you'll remember, was 89 degrees centigrade below zero, or 129 below 0 centigrade, and the high was 56.7 centigrade and 134 Fahrenheit. So the global average isn't highest plus lowest divided by 2. It's a combination of all the temperatures taken all over the land masses and at various places in the ocean. So, currently, our atmospheric gases measure up approximately 78% nitrogen, 21% oxygen, 0.9% argon, which is inert, it means it doesn't react with anything or bond with anything, and 0.04% carbon dioxide. And I know what you're thinking. With all of the things you hear on the news about global warming and carbon dioxide emissions, you're expecting it to be a lot higher. Well, don't worry. It will be. See, life on this planet, and especially humans, add carbon dioxide to the atmosphere. Other life forms can also sequester it. For example, peat moss will sequester carbon dioxide pretty effectively, like more effectively than trees even. And some life forms will eat nitrogen and pee out ammonia, and others will eat sunlight and fart out oxygen. And everything that exists, alive or otherwise, on this planet contributes to altering the atmosphere in very important ways. And the point of this video is to share sort of the coolness of that and the wonder of how everything balances each other out and alters each other and changes, rather than to scare you about global warming or anything of that nature. This video has gotten a bit long, so I'm going to call it there. And next week, we're going to deep dive into the importance of those specific gases and what our atmosphere is doing today. So please tune in then. In the meantime, like, subscribe, and comment your thoughts on this video and any ideas you have of things you'd like to see in future videos. Thanks for joining.